So we've talked a little bit about what a relation is, and it kind of leads us into this whole idea of the definition for what a function is. Now with a relation, for any x value that we had in our domain, it had to go to basically at least some y value. Whereas a function, what differs from a relation is that each member of the domain, in other words, each of your x's, goes to specifically one value in your range. So as you guys can see, we have this function machine. And in other words, for every x value that we plug in to this function, whatever this function is, it could be anything, it's going to produce some specific y value. All right. So for any one x, it's going to correspond exactly to one y value. And you can throw in a bunch of different x's here, throw it into this function, and it should produce a different y value. All right. So that's really the key difference between a relation and a function. Now, in mathematics, a lot of times we're actually studying this idea of functions. Relations just kind of provide that transition into this definition, though. Now, just for a moment, let's just say we're kind of having an analogy. Let's just say that a function right here is a pizza making line. Okay, so we're making different types of pizza based on this function. Now, for the first one, let's just say we want to make a pepperoni pizza. Well, if you think about it, the ingredients that you would need for a pepperoni pizza is obviously pepperoni. You would need maybe like some cheese. You would need like obviously dough and some sauce. So you would throw all these ingredients into the function, if you want to call it that, pizza making function. Now let's go ahead and maybe trying to make a sausage pizza. Well, if you think about an assembly line, by and large, it's going to follow the same exact setup, same exact function, pretty much like the same exact process to create a pizza. You know, there's not much difference between throwing in pepperoni versus a sausage. It kind of follows the same same kind of template. Like if you have your belts and dropping the cheese, it's putting the sauce on, you know, all that other stuff. But we are putting in a different specific x value. In other words, we're not throwing pepperonis in anymore, we're throwing in sausages. But it's following the same exact function. In other words, this is a different input that we are throwing in to this function. And as a result, it should give us a different y value, or in other words, a different type of pizza. In this case, you should end up with a sausage pizza. All right, so different inputs going through this function should produce different outputs. And that should only happen and that should just happen specifically for whatever inputs that you're throwing in. They should correspond to a specific y value or specific type of pizza. Now, how that relates with example 3 is we need to actually determine if this is in fact a function or not. So in other words, based on our definition that we just described, for every x value, there should be exactly one y value. So if we look very carefully, our first values are all of our x's. And then we have all of our y's that correspond to them. And the first thing that we really have to look for to determine if there's a function is if there are duplicate x's. Well, -4, we don't really see any -4s elsewhere. So this guy's okay. This guy has a 2. Do we see any other 2's? Oh, yes we do, right here. Well, we have this 2 going to 6 as a y value. We also see that this 2 is having a 2. Well, can that happen? Let's go back to the definition for what our function is. It's kind of like throwing in pepperoni. You throw that into the pizza making machine, you get a pepperoni pizza. Then, alternatively, that happens from like right here. This you can consider your pepperoni. Then, alternatively, you throw in a pepperoni again. Well, in theory, it should give you a pepperoni pizza if it's following this pizza assembly line, but it outputs a different item. As you guys can see, it's giving us a different item than it did before. Before it was 6, let's say that was your pepperoni pizza. Now it's giving us 2. Well, how could you throw in like a pepperoni pizza into this pizza making machine and end up with a sausage pizza? That can't happen. And as a result, for A, this is not a function. Looking at B, we see that we have Boston matching up with which team? Well, the Boston, hopefully you guys watch a little bit of sports, goes obviously to the Red Sox. If you're Chicago, we know that we have two teams in Chicago. They go to the White Sox and the Cubbies. Go Cubbies. And then finally the New York Yankees. Now, looking at this, do we have any inputs, these guys, going to two different outputs? Well, yes, we do. It happens, in fact, at Chicago. So as a result of that, this should not be happening. We shouldn't have that. So that is not a function. Because again, for any input, it should be going to exactly one output. Here we have a graph and a bunch of different points. Well, let's go ahead and label those points. So this first one is happening at -2. Looks like 1, 2, 3, 4. We have at 1. We have this guy at 0, 1. This one is at 1, 2, 3, 1. And then this last guy is at 1, 2, 3, 4, 5, 6, 6, -3. All right, now kind of following again that definition for what a function is. Do we have every single input going to a different output? Well, -2, there are no other -2, so this guy checks out, he's good. 0, there are no other zeros, so this guy also checks out. 3, 1, are there any other 3s? Nope, he's good. And lastly, 6, -3. Well, there are no other 6s, so this guy also checks out. Now you're looking at this and you're saying, oh wait, well I've got 0, 1 and 3, 1 though. How can those possibly go into the same spots? Well, if you look back to the original definition, it says, for any input in your domain corresponds to exactly one member in the range. A lot of times people actually mix these two up, but they are in fact different inputs, different x values that you're throwing in to your function and getting, it just so happens to be the same exact y value. A really, really great function that I love to share to kind of help illustrate this point is the function y is equal to x squared. Now, if you go ahead and say we have x is equal to 1 and throw that in here for x, we end up then with, let me change colors, we end up with y is equal to 1 squared. Well, 1 squared is just simply 1. Oops, it's simply just 1. So as a result, we end up with this ordered pair 1, 1. Alternatively, we can go ahead and throw in, let's just say x is -1. Well, if we throw that into our function, notice it's a different input. These guys are not the same. If we go ahead and throw that in there, we end up with -1 squared. Well, -1 squared comes out to be +1. Notice it just so happens to be the same exact y value. That can happen as long as your inputs are different. Okay? So as long as your inputs are different, you can end up with the same y value. That's okay. It's whereas if you said, I'm going to say, we're going to throw in 1 into this function, get a y value 1, and then all over here I'm going to throw in 1 again and end up with something completely different. That is a big no-no. All right, but you can have different inputs getting the same exact y values. All right. Lastly, we're looking at D. Perfect opportunity to illustrate kind of that point. There are no other -4s, so this guy checks out. -2, we see two -2s. They are going to two different y values. That cannot happen. All right, so D, this would be not a function. This guy would be a function. Is a function for C. All right. All right, so again, though, that is example 3 from our 2.1 set of notes.